What is the invariance principle? It's a good question. Very good question. Test you're studying. Anybody remember what the invariance principle is? It's a good thing to know. Anybody? Invariance principle? Absolutely, yeah. So it involves MLEs, right?
It's that, like, if it's in a formula, it doesn't affect the MLE. You can use the MLE in the formula.
Absolutely right. Yeah. So okay. So if I have, let's say theta hat is the MLE for theta. If I want to know the MLE of a function of theta, all I do is plug theta hat into that formula. So then let's say if I have some function f of theta, well, let's say f of theta is something like, I don't know, theta squared plus 3. I don't know what that would be, but regardless of what that function is, the MLE of that function is just the function evaluated at the MLE. So the MLE of f of theta is just f of theta hat. You don't have to do any other work. You don't have to take any more derivatives or anything like that. That's it. You're done. Does that bring back a memory? Okay. Yeah, that is the invariance principle of MLE. So if you have the MLE for theta, you have the MLE for any function of theta. You just have to plug the MLE into that function.
We should know this for the test?
You might want to know that for the test, yes. Yeah, so the test again is on Friday. I do have some extra office hours. I do have my originally scheduled office hours today from 10 to 11, 10:20 to 11:15 in the tutor room. Come by my office tomorrow between those hours if you would like to. Although I realized after I scheduled that we might have to be watching some March Madness while we're doing office hours. Yes. So we might be able to get through our lecture a little bit early today, in which I'll take some more questions on the exam at the end maybe. I do have your homework 5 to hand back to you, and I would strongly recommend that you take a look at the solutions and kind of have an understanding of how to do the homework problems. Are there any other questions though for now on the exam? Yes, Kevin.
For number 2b, why can you not use the table and for the expected value and plug in the x values like 1 squared times theta over 2 for e of x squared? So
which is this on the exam review?
Yeah.
What is that problem again? Can you quickly remind me? I'm just going to take a look at it.
I tried to use the definition of the variance, but you can't use that because I'm not sure why.
Let's talk about that after.
Okay.
Okay. Any other sort of big scale questions before we get started? Okay. Well, we are going to resume our discussion on Chapter 7, and I think actually finish up Chapter 7 today. So getting a little ahead of ourselves as far as the exam goes. But anyway, we're going to keep talking about confidence intervals this morning. Okay, and so remember the general setup here is that we're trying to estimate the population mean mu. So whatever the population of interest is, maybe it's all Ohio State students, we're trying to estimate some average quantity from that population. So maybe we're trying to figure out the average height of all Ohio State students, or the average SAT score, or the average whatever. Could be anything really. And so to do that, we kind of in our usual setup, we take a random sample from that population, and then we use that random sample to construct our estimate of what that population mean is. And so in Chapter 6, which you guys are studying for the exam, we talked about how to find good estimates, and now we're talking in Chapter 7 about, instead of giving just a single value, we're going to give a range of values. so that we can have some sense of how precise our estimate is. So instead of giving just one number, instead of giving just the sample mean to estimate the population mean, we can give a range of values. And so earlier in chapter 7, just do a little bit of review here before we jump into new stuff. We've sort of seen three cases, or three sort of situations to sort of motivate our discussion. We started out by saying we have a normal population in which we know what sigma squared is. So we don't know what the population mean is, but somehow we know what the population variance sigma squared is. So this is sigma squared is our population variance. And our confidence interval is as constructed as follows. So all of these are of our general form. We have our estimate plus or minus a margin plus or minus a margin of error. So plus or minus stuff. So some sort of a give us a range of values there instead of just one number. So then, of course, it's not reasonable to always assume that we have a normal population, and again, that knowing what sigma squared is not very reasonable either. And so we kind of adjusted. We adjusted for those assumptions. Next, we looked at the case where, okay, I still have a normal population, but I don't know what sigma squared is. I don't know what the population variance is. So instead, I can estimate it using the sample variance, or the sample standard deviation here. And that changes our formula slightly in that we go from having something that's a normal distribution to something that's a t distribution. And we looked at the t distribution, very similar to the normal distribution, but not exactly the same. And that depends on the degrees of freedom. So the t distribution depends on your sample size. And finally, in sort of the most general case here, if we're also drop that assumption that the population is normal, so we don't have a normal population and we don't know what sigma squared is, then as long as our sample size is big enough, the central limit theorem kicks in, and we can use that formula number 2. So the same formula that you use if the population is normal, just making sure that the sample size is large enough. Okay, so the next 2 slides I think are not in your notes, so I wish they were. So please take some notes on this, or at least have a maybe look back at the video if you'd rather do it that way. I wanted to be a little bit more clear because I asked you to do this in your homework. In your homework for this chapter, which I know you won't look at until next week, and that's fine, I ask you to make sure to sort of check conditions and make sure that it's appropriate to use the interval in each case. And so we've talked about both of these things, but I wanted to sort of formally say exactly what I mean by that. And the two conditions, if you look back at the definition of these confidence intervals, we assume that we have a random sample and that and then a few different cases. So if the population is normal, do I know sigma squared, and all those things. So the 2 questions you want to ask yourself is, first of all, do I have a random sample? So these methods are sort of based on having independent observations. That's sort of a foundational thing to these things. So we want to make sure that we have a random sample, and if it's not stated, we want to think about the sample. So is that sample likely to be a good representation of the population? So pretty much, is there any reason to think that sample might be biased? And that is going to be a judgment call if it's not stated. So thinking about, do I have a good sample in some sense? And then secondly, you want to check, kind of figure out which formula to use and figure out how to do that. So if for example, if I know the population is normal and I know what the population variance is, then I can use that first formula. If, again, we're told that the population is normal, but now I don't know what the population variance is, I can use that second variance. So I want to make sure that my population is normal there. And if I'm not told any information, I don't know what the population looks like, and I don't know what the population variance is, as long as the sample size is bigger than 30, you're all set. So you can use that formula again. When your sample is, when you have a random sample or a representative sample and your sample size is bigger than 30, you can sort of always use these things. They're sort of safe to use in many situations. So if I ask you to talk about conditions or kind of is the interval appropriate to use, this is the kind of thing you want to do. Think about what the sample, is it a random sample or is it representative? And then do a check on your sample size. or whatnot there. Okay, so one more thing you might be wondering is how do you know if the population or if the data comes from a normal distribution? So again, looking back at this slide, again we're looking at the population distribution. How do you know what that is? So if it's not stated, that is, how do you know what it is? So if your sample size again is bigger than 30, doesn't matter. You can use this confidence interval regardless in that case. If your sample size happens to be less than 30, and we'll look at some examples of this, then you sort of need to look at the data. And there's you can make a histogram, which is something I'll demonstrate here later in an example. Using your favorite statistical analysis software, we'll use JMP in this class. There's something called a normal probability plot, which is something we're not talking about in this class, but that's another way to kind of check, do I have data that's normally distributed? And then just note that the second and third choices require actually having the data set, which is not usually going to be the case, or not always the case for your homework problems anyway. In general, you should always have the data set to do these checks on. And again, we'll look at a few examples of this. But then just a final note that if your conditions don't check out, so if your sample is clearly biased or something like that, or your sample size is really small and your data is not even close to being normal, then we sort of shouldn't use these formulas. There's other ways to find confidence intervals that are sort of outside the scope of this class. But if we, as we're practicing these things, we might do the calculations anyway, just to kind of see what the interval would look like, and then keep in mind that the results may not be great. So this idea of conditions, we'll come back to this again, but it's kind of a big idea in statistics is, yes, we have these formulas, we can do these calculations, but is that a good thing to do? Is that an appropriate thing to do? And what does it all mean? So kind of keeping these conditions in mind is good moving forward. Questions or comments? Why are we even talking about this? Okay. Well, let's do another example here, and then we'll do one more example at the end to kind of show you again what I'm talking about here. Okay. So this is on page 9 of your Chapter 7 notes. So here we're talking about the Dutch Energy Agency, and they're studying the efficiency of their wind turbines. And so as part of this study, they measured the energy output for a sample of 200 of its wind turbines of a certain class, and we want to estimate a 99% confidence interval for the output of these turbines. So the DEA, Dutch Energy Agency, not the usual DEA, I guess there. And then again, kind of our usual statement, we want to make sure to check our conditions and, most importantly, interpret our interval in context. So there at the top of the page, right under the statement of the example, you have this histogram here. And you have some summary statistics from the data. So again, we don't have the data, but we can look at a picture of it and know some summary information about it. So what we know is that the sample mean from those 200 numbers is 110,221. We know that the standard deviation is 22,867. And then it gives you a number of other numerical summaries there as well. And then our sample size is 200. Okay, so let's look at calculating this confidence interval. We want a 99% confidence interval for the true average output of the Dutch Energy Agency's turbines. Okay, so we're going to use this information that we have to estimate what this true average output of these turbines is. Okay, so our first step is always to kind of check our conditions, make sure that we're allowed to use the calculations. So check conditions. Again, I have two conditions to check. So do I have do I have a random sample? So, first question for us: do we have a random sample here of these wind turbines? Doesn't say so, right? All we're told is that we just have a sample of 200 turbines. So it's not stated that we have a random sample. So it's not stated. But we're going to trust the Dutch Energy Agency. We're going to they're hopefully a reputable agency, and we'll have collected a good sample. So. But again, there's sort of no reason to assume that we would have some sort of a biased sample. So they took all their, hopefully they didn't just sample all their newer turbines, for example, or all the turbines in a certain region. We would assume that they would want to get a representative sample. So because, let's say there's no reason to assume a biased sample. So we're good to go here. Put a check mark by our random sample. So again, it's not stated that we have a random sample, but again, Dutch Energy Agency is probably going to do a good job of giving us a sample that is not biased. Okay, so we're okay there. Next, we want to make sure that either think about the population or think about the size of our data set. So here, n equals 200, which most days anyway is bigger than 30, and so we're good to go, regardless of what the data looks like, regardless of the population distribution. And again, we could look back at the histogram, and again we can see that there's definitely some skew going on there, right? It's maybe most of the data is kind of in one range, but then it does kind of tail off to the right there. So it's not perfectly normally distributed, but again, our sample size is large enough that it doesn't matter. So we're okay on this, on our second condition as well. Our sample is fine. Yeah, Kevin.
Does the central limit theorem mean that if you take more than 200 samples, it will eventually not be skewed?
Yeah. So question was, does the central limit theorem mean that if I take more than 200 samples, it will eventually not be skewed? No. So the central limit theorem tells us something about the sample mean of our sample. The X bar, for example, tells us something about that. So hopefully the population, hopefully our sample, if our sample is representative of the population, if I take more samples, it should keep looking like that. Maybe each bar will just get higher. My counts will go up, and so I'll have more numbers, but it should look something still like the population distribution, or sort of, it might be the skewed kind of a thing. The central limit theorem tells us about the behavior of the sample mean, so about X bar. So as long as I'm taking the average of enough numbers, the distribution of that thing will be approximately normal. So there's a difference between the population distribution, which looks like that, and the sampling distribution of X bar. And the central limit theorem tells us about the sampling distribution of X bar.
Okay.
Is that okay?
Because I would think if you take a bunch of samples, it should look like that. It should be skewed in some sense.
What should be skewed?
Well, the sampling. If you take a bunch of samples, I would think that even though you take a bunch of points, it should be sampled, or it should be skewed. The central limit says no, it should not at all.
So the central limit theorem doesn't tell us about the population distribution. So this is like the population distribution here. So this is like, for example, something like this, or something like house prices is going to be very skewed. So regardless of how many houses you look at and write down how much they cost, you're still going to have a skewed distribution. Again, the central limit theorem is talking about the sampling distribution. So of those let's say I look at 100 houses, or I have 200 turbines here. If I take the average of those, that thing will have a distribution that is close to a normal distribution. So it's not the central limit theorem doesn't tell me about the population distribution. That'll always sort of stay the same or about the same. Central limit theorem tells me about the sampling distribution of X bar, of the sample mean. That's a good question. Okay, otherwise? Okay. So since our conditions have checked out, we're ready to actually do our calculations. Remember our confidence interval is X bar plus or minus T sub alpha over 2 n minus 1 times the standard deviation, sample standard deviation over the square root of the sample size. Okay, so let's write down the information that we have. We know what X bar is. That comes from our summary information there. So that was the 110,221. We also know what the standard deviation is. That's 22,867. Again, that's coming from our data. So we had these 200 numbers, and we calculated the average of those, and we calculated the standard deviation of those. So won't make you do that by hand, but that's done using technology. And also our sample size n is 200. Okay, so the only thing we have yet to figure out is what this T sub alpha over 2 business is. Okay, so if I want a 99% confidence interval, what does that mean alpha is going to be? So what does alpha equal if I have a 99% confidence interval? 0.00. Okay, so that's alpha over 2, I think, yeah. So again, alpha is just 0.01, so 1% there, the rest of the area there. So T sub alpha over 2, that'll be 0.005, and my sample size is 200, so I need to find that critical value. And to do that, I can look at the table, which I did include this time. So again, I want T sub 0.005 and 199. So again, the first thing you do is you look up your degrees of freedom in the first row on the left side here, and 199 is not there. So if you're going to use the table, what do you need to do? Round down, right? So we will instead use this is going to be approximately equal to, those will be about the same thing. And again, I want 0.005, so I can go over to that column, and there we go. So our critical value is going to be 2.617. Okay. So T equals 2.617. And we are ready to go. Our confidence interval, we can calculate this thing. It's going to be 110,221 plus or minus 2.617 times standard deviation, 20,867 over the square root of 200. And if you calculate that out, that will give you an interval of 105,989.989.47 all the way up to 114,452.54. So that is our 99% confidence interval for the output of these turbines. Are we done? No? Yes, exactly. We want to make sure to interpret this thing. So again, kind of our usual way of saying this is we are 99% confident that the true average output of the wind turbines is between 105,989.47 and 114,452.54. What are our units here? Kilowatt hours. Okay, so again, we're 99% confident that the average output of the wind turbines is between about 106,000 and about 114,400 kilowatt hours. And we're done. So that's all we do here. Questions, comments? Is this feeling okay? Kind of what we're stepping through here. So I think this might feel this should be anyway feeling a little more straightforward than chapter 6. So that's the good news, at least going forward here. Okay, so that's confidence intervals for a population mean. The one other confidence interval we'll talk about here, moving on to page still on page 9, I guess, is confidence interval for a proportion. So that previous formula is great, although sometimes we might want to estimate something other than a population mean. So kind of thinking back to, well, chapter 3, I guess, in our binomial distribution. That's rearing its head again. So if we have our random variable x is the number of successes in a random sample of size n, then we know that x is going to be binomial out of n trials with some unknown probability of success. So previously we didn't know what the population mean was. That was our that was our estimation problem. And now we don't know what the true probability of success is. So again, we're kind of revising what we did formerly, where we said we knew what the parameters were and kind of did probability calculations. Now we're kind of stepping back and saying, so in a more realistic situation, we don't know what these parameters are. So the way that we can set up a confidence interval for this setting to estimate the probability of success here is we can use that normal approximation that we looked at a long time ago as well, back in chapter 3. And the main idea there was that for a binomial, so for x exactly distributed as a binomial random variable with n trials and probability of success p, it's approximately distributed as It's also approximately distributed as a normal distribution with the right mean and variance there. So mean of a binomial is np, variance is n times p times 1 minus p. Again, as long as n times p was bigger than 10, as well as n times 1 minus p was bigger than 10. So as long as sort of n and p were not both too small there. Okay, so this is an approximate distribution we have going on here, as long as our sample size is big enough here. So I think we derived this back in chapter 6 as well. A good estimate for the proportion, the true probability of success, the true proportion of success. Again, we can use kind of a natural idea. We can use the sample proportion as our point estimate. So we're going to use p hat, which is the number of successes out of n, to estimate p, which is the true and unknown probability of success. Okay, and so we can think about what the mean and variance of this estimate are. So the expected value of our estimator p hat. Well, that's the expected value of x over n times the 1 over n times the expected value of x. Again, x is a binomial binomial random variable. So what's the expected value of x? Everybody said np. That's right. 1 over n times. So that gives us the right expected value. So p hat is going to be unbiased here for the true probability of success. And let's look at the variance of p hat. The variance of p hat, by definition, is variance of x over n. Remember, if I have a constant inside the variance, I can square that and pull it outside. So 1 over n squared times the variance of x. And the variance of a binomial distribution is
P1 minus P.
Yeah, exactly. So this is n times p times 1 minus p. So we still have that n squared floating around. So the variance is p times 1 minus p over n. So that the standard deviation of our estimate is just the square root of that. Square root of p times 1 minus p over n. Okay, so that's kind of going through our usual calculations with figuring out things about our estimator here. We see that it's unbiased, and we can figure out what its standard deviation is. So what that implies is that this type of a thing is going on. So remember, here we have an estimate minus the mean divided by a standard deviation. So before that was x bar minus mu over s divided by the square root of n. Now we're just taking our estimate, which is now p hat, subtracting off its mean, which is we just found was p, and dividing by its standard deviation. And again, that's kind of our usual standardization formula. So that thing's going to have approximately a standard normal distribution. And that will be true as long as those conditions that we talked about just a minute ago check out. So as long as n times p is bigger than or equal to 10, and n times 1 minus p is bigger than 10. So this here is sort of our large enough. Well, this is sort of our large enough condition here. So how can I actually check that? Again, I don't know what p is, right? So how can I make sure that n times p is bigger than 10 and n times 1 minus p is bigger than 10? So since p is unknown, we'll just use our estimate of it. So since p is unknown, we just need to check that n times p hat is bigger than 10 and n times 1 minus p hat is bigger than 10. So the usual thing we do in this class is if we don't know, if we can't use the actual thing, we just plug in our estimate and go from there. And so this is all we have to do to make sure that we can use this interval. I guess we also want a random sample. That never goes away. That's always lurking there in the background. But otherwise, that's all we need to do to make sure we can use this procedure that I'm going to show you on the next page here. Okay, so kind of thinking about what we did back for the estimating mu, the population mean, we want to find these critical values such that this probability statement is true. So that when p hat is a random variable here still, we want this probability to be something big, 0.99, 0.95, something like that. And so what we did before was we solved this kind of a formula for mu. So we wanted the probability of to be approximately equal to 1 minus alpha, and then we solved this thing for, we solved that thing from u. That's where our other confidence interval came from. Again, you could do that again here, but it's going to give you something that's really horrible and messy. You can check out your textbook if you want to see what that looks like. So what we'll do instead is we'll make one more approximation, and this is not going to change things too much. Again, like I just said, since we don't know what p is, we can just and which again the standard deviation of p hat was p times 1 minus p over n. So since we don't know what p is there, we're just going to plug in our estimate and use that instead. So we're going to estimate that standard deviation with something called the standard error. And the standard error is an estimated standard deviation. So throw some new terminology at you there just to clarify we're talking about a estimated standard deviation instead of the true standard deviation there. Okay, and that's not going to change the distributional things that we need going on here. So here's our confidence interval that we can use for proportion. So we'll take this and run with it. So if I have p hat as the sample proportion from a random sample, so there's that coming up there again. As long as n times p hat is bigger than 10 and n times 1 minus p hat is bigger than 10, then our approximate 99%, 95, whatever percent confidence interval, the formula is right here. So again, this is still the estimate plus or minus a margin of error. And again, the margin of error is our critical value. So we have our critical value, and we have our standard error. So it's kind of the same setup as what we saw before. We're just talking about a proportion now, so the formula is slightly different. Okay. Questions, comments before we do an example? No? Okay. Okay, so to go about applying this thing, let's look at this example. So if I take a random sample of 120 fatigue failures, I find that 11 of those were due to corrosion. So I want to find a 95% confidence interval for the proportion of all failures due to corrosion. So simple example here. So my first step when I'm thinking about calculating a confidence interval, I want to make sure that my conditions are okay here. So one, do I have a random sample? And two, is the sample large enough? So do I have a random sample? Yes, duh, right? Duh. Stated. So we're good to go there. Large enough, so my sample proportion p hat is my number of successes here, which is those failures due to corrosion, out of my sample size, which is 120, and again n equals 120. So n times p hat is 11. Well, that's bigger than 10. And n times 1 minus p hat, that would be 109. Is bigger than 10, so we're all set. We're all set there as well. Okay, so well, let me leave that up here. So again, my formula, remember, is p hat plus or minus z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. So I actually only need one more thing here, and that's z sub alpha over 2. So what's my alpha in this case if I want a 95% confidence interval? Alpha is then 0.05, right? So this is z sub 0.025. And if you look back earlier in your notes, this is 1.96. So that's for a 95% confidence interval, my z sub alpha over 2 is 1.96. Okay, so then my confidence interval is as follows. Again, plugging my numbers into the formula here, I have 11 over 120 plus or minus 1.96 times the square root of 11 out of 120 times 109 out of 120 divided by 120. Let me not make that shortcut. So this is 1 minus 11 out of 120. So there's p hat times 1 minus p hat. And if I calculate that out, this is, what's this interval going to be? This is 0.0403 up to 0.1437. It's supposed to be a 1. Okay, so then again, we want to give an interpretation here, so we can say we are 95% confident again. Then what are we talking about here? We're talking about the true proportion of failures due to corrosion. So we're estimating that that thing is between 0.0403 and 0.1437. Okay, so once we've done the other things in this chapter, I think this should be feeling fairly straightforward at this point. Questions or comments you guys can think of? No? Okay. All right, well, one more thing to talk about. This is kind of same thing that we looked at before with the confidence interval for a population mean. Again, the margin of error depends heavily on the sample size, and so if I want to get a particular margin of error, I can calculate what sample size I need to get that. So here again, my margin of error we're going to call that E. Again, the formula here is z sub alpha over 2 times square root of p hat times 1 minus p hat over n. Okay, and then if I just kind of solve that thing backwards for n, I get that. So solve that top formula for n, and that's what you get. So if I want to get a particular margin of error, so I say I want a margin of error of at most 0.02 or whatever, I can just use this calculation to find out what my sample size needs to be. So if you might be asking yourself, well, if I'm thinking about my sample size, how do I know what p hat is? So if p hat is unknown, then use p hat equals 1/2. And the reason for that is this will maximize that formula there. So if you found the value of p hat that gave you the biggest sample size, to make sure that you have the right margin of error, that's going to be 1/2. So you can practice your calculus if you want to try to maximize that thing in terms of p hat. Okay, so finishing up that previous example, so what sample size would I have needed to have a margin of error of less than of no more than 0.04 in the fatigue failures example. So again, I want my margin of error E to be no more than 4. Okay, so let's say, first of all, let's say if we assume that we know what p hat is still, if we assume that p hat is what we found, 11 out of 120, which is 0.092, then the sample size I need, again, is, the alpha over 2 is 1.96 squared times 0.092, 1 minus 0.092 divided by my margin of error squared. So if you calculate that out, that'll give you 200.6. So I don't think you can find 0.6 of a failure. So what does that mean my sample size should be? 201. Okay. So if we assume that our sample proportion would somehow stay the same if we had more, if we took a larger sample, that's what we would need. If we don't assume that, we'll instead just use p hat equals 1/2, and then our sample size, again, same critical value there. So I just do that same calculation again using sort of this, not saying I don't know any information about p hat here. This will give me 600.25, so therefore I should use 601. I should take a sample of size 601 here. And so again here, when I don't assume I know anything about p hat, I need a larger sample to get that same margin of error. Okay. I wanted to do one more example that's not given in your notes, but I do also want to. Does anybody have a question about the exam? No? Okay, then let's do one more quick example where we kind of step through this whole process, and then I do have your homeworks to hand back at the end. So don't leave without grabbing that. Okay, so this is an example out of your textbook. Let's. You know what? I don't think I'll be able to do this in 7 minutes. Let's talk about this one on Monday. So come up and get your homework. We'll give you a few minutes break here for the exam on Friday, and otherwise, hope you guys have a great rest of the week. See you on Friday. Let's see, here's A through O, and here's everybody else.